Today we study protection systems in the power networks. This lecture focuses on how protection keeps the electrical system stable. You will see how faults, overloads and abnormal condition affects the networks. When you design transformer protection, you must consider the transformer operating behavior. Transformers face more than face-to-face and air faults. They also face internal winding failures. Transformer damage often results from abnormal operating conditions. Typical causes include overload, high current from external short circuits, oil level reductions without internal faults, switching operation. One key phenomenon is magnetizing inrush currents. When the transformer is energized, a large magnetizing current follows. The peak value often reaches up to 10 times the rated current. This current decreases fast. After about 0.3 to 0.5 seconds, the current falls below the rated values. Another effect occurs when the transformers disconnect without load. Energy stored creates oscillation or voltages. Peak values reach up to 5 times the rated voltage. In practice, arc reaction in circuit breakers connects limits this rise. Typically, overvoltage stay within 3 to 3.5 times of the rated voltage. During no-load switching, inductive energy stored in the system causes steer voltage increases. The highest peak occurs in the instant of the switching. Voltage increases until the arc ignition occurs between breaker contacts. This limits the overvoltage level. Actual overvoltage remain lower than theoretical values. They usually stay within 3.5 times the rated voltage. Transformer protection must also consider changes in the current and voltage phase angles. Switching operation change magnetic condition inside the transformers. As a result, current and voltage phases differ from normal operating values. These changes affect protection measurements. Measured current and voltage values differ from nominal conditions. In the electrical network, transformer protection uses main protection and backup protection. The main protection includes differential protection, gas protection, and pressure protection. Backup protection uses overcurrent protection and overload protection. For small power transformers, overcurrent protection also serves as main protection. Transformer protection design must account for electrical, magnetical, and mechanical effects. Only then does the protection operate selectivity and reliable. This section explains the operation principle of transformer differential protection. When the fault occurs outside the transformer protection zone, current flows through the transformer. The current on the primary and secondary slides are almost equal. Under the normal condition, the relay sees only a small differential current. This current equals the differential between the two measured currents. Differential current equals primary current minus secondary current. For external faults, this fault remains close to zero. Small difference come from measurement errors and transformer ratio mismatch. The relay restraint settings ensure stability. It prevents tripping during the external faults and normal loads condition. During the internal fault, the situation changes. Current in both transformer windings flow towards the fault. Their direction becomes the same. As a result, the differential current increases sharply. The relay now measures the sum of the winding currents. When the summed current exceeds the relay setting, the relay operates. The transformer disconnects from the network. The characteristics curve show this behavior. At low restraint current, the relay allows a small differential current. This avoids false trips due to errors and inrush effects. At high restraint currents, the relay requires a larger differential current to trip. This improves stability during heavier through faults. This principle makes differential protection selective. It operates only from internal transformer faults. It remains stable for the external faults and normal operating conditions. Modern microprocessor-based transformer differential protection uses current-dependent settings. These settings adapt relay behavior to operating conditions. The typical operating characteristics has several zones. In the first zone, protection uses fixed differential current settings. This setting does not depend on load currents. It accounts for magnetizing current, CT errors, and voltage regulation effects. In the second zone, the differential setting depends on the restraint current. As the load current increases, the allowed differential current increases. This improves stability during the external faults and heavy load. In the third zone, the slope increases further. This differential threshold rises faster than the second zone. This ensures stability during the high true fault currents. Gas protection is the only non-electrical protection used by main transformer protection. This protection is known as Buchholz protection. Gas protection has two stages and two signals. The first stage detects oil movement. Oil flow inside the relay indicates internal faults with slow gas generation. The second stage detects gas accumulation. Gas pressure activates second contacts. This stage sends a trip signal to the control system. Gas protection installs in the pipe between the transformer tank and conservator. The transformer tank requires a slight tilt, about 1.5%. This tilt directs gas bubbles toward the relay. Internal faults decompose oil. Generated gas flows into Buchholz relay. The relay reacts according to the gas volume and oil flow speed. Overcurrent protection uses current components as operating quantities. These components include phase current, negative sequence current, zero sequence currents. Air fault protection often uses zero sequence current. This equals 3 times the neutral current. Directional overcurrent protection evaluates current directions. This improves selectivity in mesh networks. Protection reliability improves by adding voltage blocking. The relay checks voltage increases together with the current increase. This helps distinguish fault from load changes. Busbar and switchgear are key nodes in the power system. Faults at those points must clear very fast. A busbar fault affects many feeders at the same time. Delayed clearing causes large damage at the system instantly. The simplest busbar protection uses overcurrent protection. Each feeder relay trips when the current exceeds its setting. This method has these limits. It's not selective and fault clearing depends on the time grading. And upstream breakers may trip unnecessarily. To improve reliability, arc protection is often added. Arc protection detects lights from electrical arc. Light sensors install switchgear components. When the internal arc occurs, light intensity rises instantly. Fault current flows at the same time. The protection logic checks two conditions: arc light detection and overcurrent detection. If both conditions occur, the relay trips immediately. Tripping time is very short, typically a few milliseconds. Arc protection limits damage. It reduces thermal stress, it reduces mechanical pressure, and improves personal safety. For higher reliability, differential protection is used at the busbars. Busbar differential protection compares current from all feeders. Under the normal operation, the sum of the current equals 0. For external faults, the fault current enters through one feeder. It leaves through another feeder. The current sum remains close to 0. Protection is stable. For an internal busbar fault, all feeder currents follow toward the fault. The current sums become non-zero. Differential current rises sharply. Protection trips all connect and breakers. This method provides highly selectivity, very fast operation, and clear separation between internal and external faults. Modern busbar protection often are combined. Differential protection as main protection, arc protection for ultra-fast clearing, and overcurrent protection as backup protection. This combination ensures fast, selective, and reliable busbar protection. Arc protection uses light produced by an electrical arc as the operating signal. An electrical arc creates strong light pulse during the fault. The arc protection scheme installs light sensors inside the switchgear. This sensor monitors a compartment where internal faults may occur. If at least one light sensor detects an arc flash, the protection logic activates. The relay issues a trip command. To avoid false trips, arc protection works together with the overcurrent protection. The logic follows two conditions: light detection from an arc and presence of fault currents. When the both condition occurs at the same time, tripping is allowed. The circuit breaker opens immediately. If light appears without faulty current, the relay blocks tripping. In this case, the breaker remains closed. This prevents incorrect operating due to internal light reflections. Busbar differential protection works as a different principle. During the external fault, currents entering and leaving the busbar balance each other. The sum of currents equals to 0. The relay does not operate. During the internal busbar fault, all feeder current follow toward the fault. The current balance is at lost. The differential current appears. When this differential current exceeds the setting, the relay trips. All connected circuits breakers are opened. Arc protection provides very fast fault clearing. Differential protection provides high selectivity. Together, those protection ensures fast selectivity and reliable busbar fault clearing. System protection supports stable operation of the power system. Its goal is to prevent system collapse and large disturbances. In distribution networks, two system protections are mostly important: load shedding protection and power switching protection. Load shedding protection reduces system load during abnormal conditions. It operates during frequency or voltage declines. A drop in active power causes frequency reduction. This happens after generator disconnection or loss of supply. If spinning reserve is inefficient, system frequency falls. This affects the entire power system. Reactive power deficiency causes voltage drop. Voltage decreases locally in affected network areas. Based on this behavior, two load shedding types exist: under-frequency load shedding and under-voltage load shedding. Under-frequency load shedding protects the whole power system or island synchronous area. Under-voltage load shedding protects a part of the system with reactive power deficit, such as a substation supply area. Both protection operates in the steps. Each step disconnects a defined load portion. For each step has its own frequency or voltage threshold and time delay. Frequency and voltage normal values define reference points. Both protection includes load restoration logic. When the frequency or voltage recovers, load reconnects according to the preset sequence. The protection monitors system conditions during the reconnection. The required amount of load shedding depends on the system sensitivity. Sensitivity describes how frequency and voltage responds to load change. This relationship is described by load characteristics. Active power versus voltage and frequency. Reactive power versus voltage and frequency. Active power depends mainly on the frequency. Reactive power mainly depends on the voltage. Typically, reference values include nominal voltage and nominal frequency. Frequency sensitivity of the active power is usually higher than the voltage sensitivity. Voltage sensitivity of reactive power is significantly higher than its frequency sensitivity. These characteristics define the operation points of load shedding protection. Under-frequency load shedding operates when system frequency drops below a set value. The protection reacts to the frequency decline caused by active power deficit. When the frequency falls, the protection disconnects part of the load in steps. The goal is to restore frequency at its normal value. This protection must act both as the entire power system and for island areas. For this reason, under-frequency load shedding installs at the many substations. The scheme is distributed and multi-staged. The amount of loads disconnect depends on how much the frequency drops. A small frequency deviation requires less load shedding. A large deviation requires more load shedding. The required shared loads is calculated using statistical frequency characteristics of active power. The load to be disconnected is defined as a formula, where P0 represents frequency independent loads. P1 and P4 represents loads with different frequency dependence. Each coefficient describes a specific type of load. P0 represents frequency independent load, such as electrical heating and base loads. P1 represents metal cutting machines, fuel pumps and compressors. P2 requires network transformers. P3 and P4 represent low and medium and high pressure pumps and ventilators. Those loads form the main auxiliary consumption of thermal power plants. As a frequency decreases, frequency dependent loads change their power demand. The protection uses this relationship to calculate how much load to shed. By shedding the correct amount of load, the system stabilizes frequency. This prevents generator tripping and large-scale system collapse. Under-voltage load shedding restores voltage when the voltage drops below normal values. The protection disconnects part of the load to support voltage recovery. Voltage reduction results mainly from reactive power deficit. This deficit causes local voltage collapse in the network areas. Voltage decline develops slower than the frequency declines. It causes less immediate disturbance of the overall system. Reactive power deficit is easier to compensate than active power deficit. Synchronous generators increase reactive power by raising extinctions. Automatic voltage regulation supports this process. Synchronous motors also increase reactive power demands when voltage drops. This behavior limits voltage recovery. Generated reactive power is increased has technical limits. Extinction current cannot increase indefinitely. If voltage decline occurs far from generators, generator response becomes insufficient. In this case, voltage control alone cannot restore voltage. Under voltage load shedding becomes necessary. The protection disconnects part of the load to reduce reactive power demand. The amount of the load shed depends on the depth of voltage drop, sensitivity of the load, voltage balance between reactive and active power. Under voltage load shedding operates in steps. Each step has its own voltage threshold and time delay. By shedding the current amount of load, voltage recovers to acceptable levels. This prevents prolonged voltage instability and equipment damage. Most electrical loads consist of induction motors. The torque of an induction motor is proportional to the square of voltage. When the voltage drops, motor torque decreases. If torque falls below the load torque, the motor begins to slow down. The voltage at which torque equals load torque is called the stall voltage. Below this voltage, the motor cannot maintain speed. During the voltage reduction, the motor slows down and their slip increases. As slip increases, motor current increases. Even at a small voltage drop has a strong effect. At the voltage decrease about 0.2 per unit, induction motor current approaches the starting current. This current is roughly 5 times the rate current. High motor current causes additional voltage drop in the network. This accelerates voltage decline over the wider area. The process can spread quickly. It may lead to voltage collapse of a large part of the power system. Under voltage load shedding prevents this situation. By disconnecting part of the load, voltage collapse is avoided. System stability is restored. After active and reactive power balance recovers, load restoration starts. Load restoration automation reconnects loads gradually. The reconnection sequence works opposite of the load shedding. Load reconnects step by step while monitoring voltage and frequency. This controlled restoration prevents repeated voltage collapse. It ensures stable operation after disturbance. Circuit breakers are a mechanically complicated device. Even with the continuous supervision, the breaker may fail to operate. Breaker failure protection ensures system protection in this case. It operates when the main protection issues a trip command, but the breaker contacts remain closed. When the breaker fails, backup protection must act. Backup protection sends a new trip command to the disconnected defaulted section. Pure backup protection is slow. It depends on large current values and time delays. Selectivity is also limited. For this reason, breaker failure protection is used in the substation. It provides faster fault clearing. Breaker failure protection detects small residual currents. It operates faster than the backup overcurrent protection. The operation principle is simple. The main protection sends trip signal to the breaker. A timer starts at the same time. If the current disappears within the set time, the breaker opened correctly. Breaker failure protection resets. If the current remains after the set time, breaker failure protection operates. It sends a trip command to the upstream breaker. In the example of scheme, breaker failure protection is applied to breaker VL2. Current relays K1 and K2 measure the same current. Relay K1 has a longer operating time than relay K2. Relay K2 operates first. If the current through breaker VL2 exceeds the pickup value, relay K2 operates. It sends a trip command to breaker VL2. If the breaker VL2 fails to open, current continues to flow. After a longer delay, relay K1 operates. Relay K1 sends a trip signal to the upstream breaker VL1. This isolates the faulted section. In this scheme, a relay acts as a backup for the relay K2. Breaker failure protection ensures fast and reliable fault clearance when the breaker does not operate. We have reached the end of this lecture. You saw how frequency and voltage behavior affects system stability. You learned why load shedding is necessary and how to prevent collapse. You also learned how to breaker failure protection ensures fault clearance when equipment does not respond. Protection is not only about tripping, it's about keeping the system stable and safe. In the next lecture, we will build these principles. We will apply them to the real protection settings and coordination examples. Review the key concepts before the next session. Focus on cause and effect. Thank you for your attention.